10.2 Alkanes. Alkanes are organic molecules that contain carbon-to-carbon single bond. The ending "ane" means that they are single bonds. So when we're talking about an alkane, we're talking about organic molecules with single bonds. And then we're going to be more specific, and we name them by using the number of carbon atoms connected in the longest continuous chain. Commonly used as fuels, whether it's for heaters or cooktops or your gasoline, whatever. Now, here's the first 10 prefixes for our alkanes. You'll notice I'm going, you must memorize these. Well, here's why. Not that if you don't memorize them, I'll slap your hand. That's not why at all. If you don't memorize them, you won't know how to name the organic molecules, because even though these are just the prefixes for the first 10 alkanes, this is the starting block for naming all of our organic molecules. So if you don't know these first 10 prefixes, then you can't do anything else essentially along the way, the rest of the way. So that's why. Now, you go, I can't memorize the 10 things. Well, you already know most of them, so let's think about this. Right? You've heard of meth. Little did you know that meth, the prefix, means one carbon. Well, methane means one carbon, all single bonds. You might not have heard of ethane. Okay, I'll give you that one. All right, so two carbons. Propane, well, everybody pretty much might have seen a propane tank. You have it hooked up to your barbecue grill maybe. Well, propane represents, the prop stands for 3 carbons, the ane, all single bonds. You've heard of butane. Well, there's your butane has 4 carbon atoms, and it's all single bonds, so that means it's 10 hydrogens. Now, pentane, you may not have heard of pentane, but you've heard of the pentagon, and the pentagon has 5 sides, so, 5. Pent means 5. And so pentane, a compound with 5 carbons and 12 hydrogens. Hexane, a hexagon has 6 sides, so hex, 6, and hexane, all single bonds, so C6H14 is hexane. Hept stands for 7, so our heptane, 7 carbon atoms, all single bonds, so C7H16. Octane, an octopus has 8 arms or legs, whatever they are, and so octane is carbon with is a compound with 8 carbon atoms, and so because it's all single bonds, that puts it at 18 hydrogens. Now, nonane you probably haven't heard of, so you do have to think about that one and go, okay, I'm going to have to memorize that one because I've never heard of that one. Okay, so here's nonane. Well, that's 9 carbons. So since it's ane, all single bonds, it's 20 hydrogens. Now, decane, you may go, I've never heard of decane. Well, you've heard of a decade, and that's 10 years. So deca. Okay, so 10. So decane is 10 carbons and 22 hydrogens. Now, you may go, how in the world do they figure out how many hydrogens? Well, if it's all single bonds, there's a nice formula. C10H2N plus 2. So CnH2n plus 2. So if we had 10 carbons, to figure out how many hydrogens there are, it would be 2 times 10, which is 20, plus 2. So that's how you would figure out how many hydrogens there were for each of these if you didn't want to have to count them out. So like propane, for example, you go, well, how do we know there's 8 hydrogens there? Well, propane has 3 carbons. So our formula is Cn, so N stands for, in this case, if we're talking about 3 carbons, okay, so Cn, C3, H, so 2, and 2 times 3 is 6, plus 2 is 8, so C3H8. Now we're going to look at different ways to write these formulas. So in a condensed structural formula, you have a carbon atom and its attached hydrogen atoms, and they're written as a group. And so the carbon that has this 3 hydrogens, right, going away from it, the 3 hydrogens are written attached to the carbon. Why? Because, well, A, that's how they do it, but B, it's attached to that particular carbon. And so on our next carbon, our second carbon, in, notice it has a bond to this carbon, it has a bond to that carbon, so that takes up 2 carbon 2 single bonds. So that means, since we know carbon always likes 4 bonds, then that means it only has a spot for 2 hydrogens left. That's why there's only 2 hydrogens here. And so these 2, one would be up here, one here. But we're not going to take up all that space, and we're going to write them condensed next to the formula here. So when we look at this carbon here, it's connected to that carbon, it's connected to that carbon. So it has 2 bonds already, so we know carbon atoms like 4 bonds, so it can only have 2 more bonds. So 2 hydrogens would be here. We represent that here. And then our last carbon at the end is attached to 1 carbon. So that means, since carbon's like 4 bonds, it's going to need 1, 2, 3 hydrogens. And so we have 3 hydrogens attached to it. Now, you don't have to write the dashes between it. It can also be simplified without the dashes, and quite often when I'm writing it, I'm going to not write it with the dashes because the dashes just take a little bit longer to write. So alkanes are written with structural formulas that are expanded so that you could see each bond, or condensed. So you'll notice that when we're writing the CH3, it really is this way. Well, that's even a squash spider view. It really is the tetrahedral shape, but that's way too much trouble to draw. So this is a simplified way, and then to even further simplify it, we're going to have the condensed. So need you to realize when we're writing it CH3, it really is this. And then when we have a CH2, this carbon here is attached to another carbon, probably, and so we have a hydrogen here and a hydrogen here. Now, then, to make it even more condensed, they can even do a line formula. These are called line formulas. And you go, what the heck? Well, each end or corner is going to represent a carbon atom. Now, because hydrogens are just kind of, I'll just say, stuck on there, and we know that carbon always likes 4 bonds, so if the carbon here, if we just have an alkane, that means we just have a carbon and hydrogens. So this line needs to show a couple of items. It needs to show how many carbons, and of course if we know how many carbons there are, we can calculate how many hydrogens. And they also want to show that the tetrahedral shape is still retained. And you go, all that does is look like a zigzag pattern. I know, but anyway. So let's look and see how what in the world this represents right here. So this end represents a carbon, this turn represents a carbon, this end represents a carbon, this corner or end represents a carbon, and this is another carbon. So you count that up. 1, 2, 3, 4 carbons. Well, we know the prefix for 4 is but, and this is all we are told that this is an alkane, so this is going to be butane. So now then, to kind of summarize all the different ways that our organic molecule can be represented. So here's hexane. So hexane, hex is the prefix for 6. Ane means all single bonds. So, realistically, this is the most realistic version here because it's showing the tetrahedral shape. But again, it's still, quote, ball and stick model, meaning that if you just had balls and sticks and put them together, it would be that. All right. If we were to just show C6H14, that is really, that's just the molecular formula. It really doesn't tell us a whole lot about how they're rearranged. And so that's why we don't write our organic molecules as a whole as just C6H14. That's why we go to all this trouble to show how, whether it's the expanded structural formula or the condensed. Notice here, this condensed structural formula is ziggy-zaggy, and you're going, why? Well, look up here at the ball and stick model. Because it's tetrahedral shape, it's like this. But in all honesty, when we're writing it with a condensed structural formula, we're not writing it ziggy-zaggy like that. We're either going to have a straight chain or a straight chain without the dashes or the structural formula. Now notice here on the structural formula, count to make sure that there's, a total of 6 here because this is hexane. So 1, 2, 3, 4, 5, 6. Yep. So notice here that if we had 4 carbons and 10 hydrogens, there are different ways that this could be represented here. Okay. I don't understand what the 9 is. I think that's a misprint, so just ignore the 9. So as a whole, we're going to look at the expanded structural formula, ignore all these condensed structural formulas. So we have the expanded structural formulas are down here at the skeleton formulas. Otherwise, ignore this whole section on condensed structural formulas here, because that's some misprint. So, please press pause and see if you can do this. All right, so here we have our carbon and our hydrogen, so we know it's an alkane. 1, 2, 3, 4, 5. So 5 carbons. The molecular formula is C5, and we could count up how many hydrogens there are or use our formula for an alkane, which is however many carbons there are, it's 2 times plus 2. So 2 times 5 is 10 plus 2 is 12. Or just count up all how many hydrogens, so that's C5H12. So we know that that's not really how it's quite often written. It's quite often written in the condensed structural formula like this. So we have CH3, CH2, 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 CH3. And its name is pentane, 5 carbons. So press pause and see if you can do the same thing for ethane and heptane. All right, now cycloalkanes are different in the fact that it is a cyclic compound. Cyclic meaning connected in a circle. So look down here at the cyclopropane. Notice how it is connected in, you go, that's not a circle, it's got 3 corners. Well, that's as circle as you're going to get for something with 3 sides here. But it's a cyclic compound. Notice how it's going to differ than this chain here, just propane. Let's see. First of all, it's not all connected. The propane is not totally connected, whereas this cyclopropane is totally connected. Well, in so doing of having a connection here, it had to give up 2 hydrogens to form this bond. So you'll notice that the formula is different. So we have, for however many carbon atoms there are, the amount of hydrogens is just 2n. So cyclopropane is a cyclic compound. So if there's 3 carbons, there are 6 hydrogens. Whereas propane, we have for the 3 carbons, we have 8 hydrogens. When we name it, we are going to say cyclo, and then however many carbon, and then single bond. So cyclopropane. So if we look at some different cycloalkanes, so here's 3, so here's our cyclopropane, and quite often it's much easier just to draw them in their figures. So cyclopropane, okay, is represented by this triangle. Why? 1, 2, 3 sides. Cyclobutane, 1, 2, 3, 4 sides. Cyclopentane, 1, 2, 3, 4, 5 sides, and cyclohexane, 1, 2, 3, 4, 5, and 6. So it's just much easier just to draw them like this than having to draw the condensed structural formulas and having to put that all in there. It's kind of a pain in the rear. So press pause, see if you can give the name for each of the following compounds. So let's look at this. We have on A, we have this straight line, this line, the line formula. Let's count how many carbons are here by knowing how to count it. So here's 1, this is an in, so it represents 1, 2, 3, 4, 5, 6, 7, 8. So that is octane. All right, so now then, let's look at this one. Well, it's a cyclic, it's all in a ring, so we know we got to start with the word cyclo. Now then, let's count how many corners there are. 1, 2, 3, 4, 5. So it's cyclopentane. So now then, press pause. See if you could name the following compounds. So we have 4 carbons, so that's butane. Here's our triangle here, our cyclic compound that has 3, so cyclopropane. Let's count up these amount of carbons, 1, 2, 3, 4, 5, 6, 7, 8, so that's octane. And here's our cyclic compound, so cyclohexane.